Oh, hi everyone. I'm back. It's a 9:23, and we started the recording already. And again, I'm sorry if I went over time, but this was not re was really required. Now we're heading into our last example. So you see on my screen, example number 4. That's our last beam design example. And this one is, if you guys remember when I said I designed my lecture to go for from a unrealistic like beam design, where somebody will give you the moment, and you go from there and you find the moment. And then example number 2, then some loads they were given to you on a cantilever beam, and you find the moment on your own, and then you design your beam. Then question number 3 was not a cantilever, it was a simply supported beam, where also some loads are given on the beam, and you will have to find the moment. And once you know the moment, then you can design your beam and so on. However, I can tell right away that those three, they are not really 100% realistic. Really, the one which is realistic, if you were to do a design, that's what you will see and what you get. So please look at the screen, and I'm going to spend some time to explain what do we have on this screen. So what we have is a plan view. So what you see here is a little plan view, not very complicated, just like a little, let's say, mezzanine, while you have an arrangement of beams and columns, a slab to support one floor. Okay, just let's get some time to spend some time to get ourselves familiar with the system. So basically, you can see we have grid lines. So please understand that we have grid lines, horizontal, which is 1 and 2, and vertical grid lines A and B and C. We also have some dimensions on the grid line. You can see between 1 and 2, there is 5 meter center line to center line. Between A and B and C, there is 7 and 8 respectively meters. The system the system is supported on how many columns? You can count the columns. So the columns are, we have a total of 6 columns. The column dimensions are marked on the label. I know that there are some of them, they are trimmed on the very bottom, like 250 by 400 and 250 by 800 on the corner, bottom right corner. But we have all the column dimensions. The columns are, again, we have total of 6 columns. You can see them, they are being shaded, the 6 columns. And then how many beams? How many beam we have? So I know some of you will say we have 4 beams. We have 4 beams. A beam which is here is here. That's one beam, and this another beam, and this another beam, and this is a fourth beam. But that's not true. So really, what we have is we have only 2 beams. We have 2 beams. So we have one beam that goes all the way from, maybe I can draw a line. So I'm going to show you here. That's one line. So that's my first beam here. So this is beam number 1, which is happening on grid line 1. And then another beam here on grid line 2. Okay, guys, we don't call the beam by the span. We call a beam because this is a continuous beam. Although it has 2 spans, but it's one beam, one single beam. Okay, we'll talk about this one later on. But for now, we have 2 beams. Then finally, we have here a slab. You know what? Probably it's better to show you because I am trying to make everything with my Revit. So here is my Revit model for my slab. So hopefully this will give you a better view of the problem, huh? Okay, so I'm just looking from the underside of my slab. You can see we have a beam here, and this beam has 1, 2, and 3 columns. And then on the other side, we have the same thing, copy and paste, 1, 2, 3 columns, and my beam is continuous on top columns. And finally, this guy here is my slab. So that's my slab, and the slab will simply support it on the beam. Something also I need to mention right now, and probably all of you know that. So the load that goes into the slab will simply carry the load, will bridge the load to the beams, and the beam will bridge the load to the columns, and finally, whether we have another floor or maybe there's a footing here, the column will deliver the load to the below column or to a footing. Okay. Again, maybe another rotation so you guys can see what's happening here. So this is my problem here in 3D. Okay. Now let's go back to our plan view. So few information you're given to you, which is really the whole problem will focus on designing the beam on grid line 1. So where is grid line 1? Here is my grid line number 1. Okay. Now, when we design the beam, we will use 25 MPa concrete, which is the norm. We have some information about the loads. So the loads here, we need to make sure that my beam is strong enough to carry the 4.8 kPa that goes onto the slab. So maybe this is storage, because for storage, we know that the minimum requirement for the live load is 4.8. Also, there is something we discussed and we talked about it, which is here. So there's something called SDL. So what is SDL? It is called superimposed dead load, which is any dead load that's not self-weight. So if we forget about the self-weight of the beam or of the slab, then we call those superimposed dead load. And you guys know that this includes partitions, includes flooring, includes mechanical, electrical. Those are everything. And from the experience, we kind of know that we need to give them some allowance. So the allowance for SDL here is 1.5 kPa. I need to remind you that whenever I say kPa, it means kilo Newton per meter square. It means every square meter. So I'm going to draw a box here. Every square meter on my floor will simply have this much, like 1.5 kilonewton of SDL, and then 4.8 kilonewton of live load. Now I said here, refer to plan view to all dimensions. So if you wonder what's my column dimension, here is my column dimension. If I wonder what is my beam dimension, so here is my beam dimension. If I wonder what is my slab thickness, here is my slab thickness, and so on. Okay. If I wonder what is the span of my my beams, so you can see that we have dimensions here 7, and then we have 8, and then we have 5. But you just have to be observant and see where this dimension ends. You can see here my grid line is simply at the edge of my slab, and the 7 meter goes from the edge of the slab to the center of the column. Some extra information, which is use 20M for your beam main reinforcement. And you can see, I didn't leave this open for you. So instead of you scratching your head, should I use 15M or 20 or 25 or 30? Very clear, use 20M when you design your beam. Also, we will use 10M stirrups. We need that. And our cover is 30 millimeter, and the aggregate size is 20 millimeter. In your design, you will need all those information for sure in the right order. Now, one more thing to guys to understand, I showed you here an elevation view. So you can see here, I cut section. You see AA, you see the AA. So section AA is here, and the section AA goes through the slab, and this is how section AA will look like. Okay. So also what I want you to do is look at the the grid lines A and B and C. Look at the dimensions, where they start, where they end. You also can see the slab thickness here. It's a 250 millimeter, and the beam thickness is 650 millimeter. And remember, they are measured from the same level, because this point is TOS. What is TOS? Anybody knows what's TOS?
Top of slab.
Thank you, sir. Okay, thank you. That's correct. Okay, and so we'll come back to here in a few minutes, but for now, please take a moment and look at the side and cross section AA. So this a section through AA, and see if it makes sense for you. Okay. Now we'll come back later on. There is some information here that you don't need for now, which is the elevations. So those are the column. They start from level number 1, which is at 0, and they go for 3 meter. So the level of the top of the slab is 3,000. It's not needed for this exercise, maybe needed for some other exercise, but not for this one. Now you can see, guys, here, if you go back, and I want to show you clearly what is the difference between this problem and the previous problem. Look at this, please. So in the previous problem, I'll show you what was given to you. So what was given to you in the previous problem is, look at this, please. It is this number is given to you, and this number is given to you. The linear load that goes into or on top of your beam. Unfortunately, for this problem here, those numbers are not directly given. You have to work a little bit to produce and create those numbers. Okay? Are you guys following? I need to hear some noise.
Yes.
Yeah, we're
Okay.
here with you.
Okay, so guys, not super science, but you have to be patient and understand just how I find those numbers. Not very difficult, not super science. So number one, I'm saying here, what is the self weight of my beam? So the self weight is function of concrete dimensions, huh? So simply the self weight of the beam is function of the concrete dimensions. Do I have to think about the concrete dimensions? What do you think? Should I, figure out what is my H or what is my width of my beam, or those numbers are completely given to me? What do you think? Hello.
Concrete dimension or your beam dimension.
Again, there is concrete dimension for the slab, there's concrete dimension for the beam, there is concrete dimension for the column, but we're designing the beam. So I want to talk about the self weight of the beam. Do I have to figure out those myself, or those are given to me?
They're given.
They
Yeah,
are
they're
given.
given.
Again, please, in the exam or midterm or assignment or anything, before you say something, just read the plan view. If those are given to you, please don't assume anything else. I get really so mad when I see students, what they do is they just go ahead and use the table. Remember the table that I taught you on how to find the thickness of the beam or the depth of the beam? Don't use this one. Use it only and only if the depth of the beam is not given. However, in this our problem here, the depth of the beam is given 650, and that's on the plan view. If you don't know where, it's over here. Huh? Actually, two times. You can see it's over there. It's 250 by 650, and also in the cross section, you can see the depth of the beam is shown over there, 650 mils. Okay, so please don't waste your time in the exam. It is given to you. All you have to do is figure out the self weight, and how we do it. We use the width of the beam times depth of the beam times 24, or y24. This is the gamma concrete, the density of concrete, 3.9. And please, do not multiply this number by the length of the beam. We want to find the self weight of the beam per unit length, not the entire weight of the beam. Because some people, what they do is, so okay, you know what? They say, this is the beam, looks like the beam is 15 meter, 7 plus 8, so I need to multiply times 15. Do not multiply by 15 meter, just find the self weight per unit length. Okay, what's next? We need to find the self weight of the slab. And you can see it's over there, slab self weight. If you go back to the lecture notes, you will see at some point I showed you how to find the slab self weight. All you need to know is what is the thickness of my slab. Okay, so if the thickness of the slab again is mentioned twice, one time here on the cross section 250, and also on the plan view, do you read the label 250 mil slab? So it's very simple. You take the 250, you multiply by the same gamma concrete. But I want you to understand that here I found the self weight of the beam per unit length. For every meter of the beam, the weight is 3.9 kilonewton. How about this number, 6, this number? This number is the self weight of the slab per square meter. And I'm very clear, I said kVA, and then I said kilonewton per meter square. So which means if you take a meter by meter on the slab, the weight will be 6 kilonewton. Okay. There is something we discussed early on, probably a month ago or more, something called the trip width. And again, if you follow Corwin class, I bet you that he discussed tributary width or tributary area. Okay, now let me see. Let me go and see. When we design this beam, look at this beam, guys. So we have beam along grid line 1, grid line 2. Now, this beam, number 1, it has to support itself, if you agree. It has to support itself. In addition to supporting itself, it has to support a portion of the slab. A portion of the slab. Okay? How much of the slab this beam is supposed to carry and support? Not very difficult. You can see the slab is supported on 2 beams, so every beam will take care of half of the slab. Now look at this number on the right, this 5 meter. So the center line to center line distance is 5 meter, which means if I put here a line in the middle, a line in the middle of 5 meter, guess what? I'm probably need to change the line type to this, for example. So what happened is, if I put same dimension, so this beam will simply take care of this much, which is simply 2.5 meter, and simply the other beam will take care of the rest, which is from here to there, and simply your beam, this beam on the bottom, will take care of 2.5 meter as well. In this exercise, your trip width is 2.5 meter, which is half of the spacing between the grid lines. Guys, remember those beams are edge beams. Edge beams. Why edge beams? Because simply there is no slab on the north side or on the south side. That's why we call them edge beam. They are at the edge. How about if the beam is central beam? Please go back to probably when I talked about trip width or trip area, and you will see if the beam is not edge, it's central, it means it will take some from the left and some from the right, and this way you get your trip width. There is example by number on my slides. Please refer to that. Okay. Now, next is after you figure out what is the beam self weight and the slab self weight. Here we go. What you have to do is you say I already wrote the equation, so there is no confusion. I say here self weight, slab self weight plus SDL. You have to add the self weight of the slab, not the beam, the self weight of the slab plus the SDL. You add them together, and then finally, after you add them together, you multiply by the trip width. Why is that? Because simply, as I said, if we go to the plan view, we said here that this 1 meter, it carries 6 as self weight, so 6 kVA as self weight, and then plus it has 1.5 as SDL. But remember, my beam is not supporting a 1 meter. Remember that from here to there, this is how much? This is 1 meter. However, my beam, you can see it's not carrying 1 meter, it carries 2.5, and that's where the 2.5 plays. So then you have to multiply the sum of the self weight of the slab plus SDL, you have to multiply by the trip width. Then finally, we add to that the self weight of the beam self weight. And please, look at this, never, ever, ever, and I'll write it here for your notes, okay? Do not multiply by trip width. Because what happened is some students, what they do is they don't know what they are doing, and they come back to your beam, self weight of the beam, and they multiply by 2.5. Think about and you will see. Do not multiply the self weight of the beam by 2.5. We only multiply the weight comes from the slab by 2.5. Anything else, don't multiply. And here is the number. So the number is 22.65. That's the total dead load going to your beam as the linear load. And then simply for the live load, same deal. The square meter carries 4.8 kilonewton. But my beam is not carrying 1 meter. It carries 2.5 meter of the slab. So you have to multiply your live load intensity times your 2.5, get 12. And then finally, as usual, what we do is we simply have to go through load case number 1, load case number 2, and which is 1.4D or 1.25D plus 1.5L to get my W factor. Finally, guys, this number is the one that goes into my design. Now, probably I'm gonna stop soon, but let me ask you. Now we have WF. If you guys remember, if you go back to question number 3 and number 2, you will see I simply threw WF into what? Into one equation. I'll show you guys. So you can see, I'm referring to this, huh? So here I used WL squared over 8. So whatever I got from load combination, 6.81, I took it and throw it here in this equation, 6.81 multiplied by the span square divided by 8, and I got moment. And if you go to the question number 2, I used WL squared over 2 because it's cantilever, huh? Because it's a cantilever. Here I use 0.8 because simply supported. Let me ask you, and probably this will bring us to the closure for this class. Now, should I use WL squared over 8 or over 2? What do you think?
Over 8.
Over 8. Any other inputs?
Over 2.
Any other inputs? Over 2 or over 8? Okay, so looks like nobody is following because it is neither over 8, neither over 2, because the beam is not simply supported. And you know what? How clear? I cannot be more clear like that. I wrote the equation and I cross it because simply I said here the beam is not simply supported. So what is the beam exactly? What is this beam? What do we call it? Is a cantilever? Is it simply supported or something else? Let's see what is my beam. Okay, again, look at my 3D model and probably will know. Now, guys, look at this beam. This beam is simply supported or cantilever or something else. Does anybody follow my discussion before?
It's something else.
Do you know, guys, Gord, do you know the name? What do we call this beam here? That doesn't have a single span. It has 2 spans and supported on 3 columns.
Not off the top of my head.
It's called continuous beam. Continuous beam. Continuous beam. Do you remember this name?
Yeah. So in this case, sir, you have to do the moment diagram, the bending moment diagram, to get the maximum moment.
Are you asking me to do that? Are you asking a question or you're confirming?
I'm asking question.
Can we design without bending moment?
No.
So
So that means we have to do the bending moment diagram.
Okay, so yeah, it's true. Yeah, we have to do that. So guys, look at this, please, so you can see, as Jelly said, you know what? Here is my beam. The beam is a continuous beam, and please, let's agree. If I see someone, I did my best to make it clear, and hopefully it's clear enough. My beam is not simply supported. It is a continuous beam of 2 spans going on 3 columns. Okay, and as I said, you cannot do the design while you don't know the moment. Makes sense, huh? We cannot do the design while we don't know the moment. And the moment is, first of all, here is some information. So the beam is continuous beam. Hopefully everyone agrees. It is 2 spans and it is statically indeterminate. I know this is long shot, like it was long time ago when I talked about statically determinate and indeterminate. Okay, do you guys remember that? So it's one piece, so which means I have 3 equations, but unknowns will be more than the equations, which means statically indeterminate. And one of the solution is to use SAFI. Okay, SAFI will find for you the bending moment on a statically indeterminate structure. Okay, the problem is live load. Live load can occupy the entire beam or one span at a time. You guys following? The live load can be on the entire beam or can be on the left span or can be on the right span. And our job as designer, as an engineer, we have to make sure that we are covered. We cover all the possible loads. Think about it as class, huh? So students in this class, but not in this class, and sometimes in the 2 classes they will have students. Okay, so live load is creating a problem. That's why we need to try all live load patterns. I had this discussion before, like in my slides, and I'm doing this one more time here. And by the way, when we do the design, our design should not be based on a single diagram. So don't ever think that I'm going to do one load pattern, so live load on both, then I can do the design. Not really. What you have to do is you have to try all live load pattern. Every load pattern will simply give you a diagram, and really our design should be based on something called the envelope, which is here. So this guy here is called the envelope because you can see Look at this, please. Give it some time, and you will see how many diagrams do you see? How many diagrams do you see?
Like 5.
Why you say 5? I know it's kind of confusing, but okay, you know what? I know that's a difficult question. Those are 3 different diagrams. Okay, because remember, the continuous beam, don't say that this is a diagram, huh? The continuous beam, this guy and this guy, continuous beam, so it's 1 diagram. So what you see here is a 3 diagram. Corresponds to what? Corresponds to live load covering the entire beam, left and right. And then another diagram that live load covers the left span but not right span. And a third one, the live load covers right span but not left span. Okay? And guys, let me ask you, the red ones, the interior line, those are diagram. How about the blue one? Do you see the blue, which is the maximum? This is called envelope. So what you see here is called envelope. Envelope, it means maximum. It means at any given section, your moment will never exceed what you see. For example, what is the maximum bending moment negative? Look at this. It's going to be from here to there. This is the maximum negative bending moment on top of your column, intermediate column. How about what is the maximum positive bending moment on the left span? It is here. This is the maximum positive bending moment on the left span. How about what is the maximum positive bending moment on the right span? It is from here to there. Okay, and you can see in between, and I make it transparent because you can see there are some other diagram which is not maximum, and simply in our design we don't use them. We just have to use the maximum, so my beam will be safe no matter what. Are you guys following?
Yeah.
Okay, I guess it's 9:50 and we both need a break, so I will stop now and we will continue after your fantastic midterm exam on Thursday. So we'll continue the discussion on Monday. Okay, we'll see you guys in 10 minutes. Thank you.